Our third presenter is Anant Telikicherla. Hopefully I didn't do that too bad. So welcome on stage.
Thank you. Okay, good morning, everyone. My name is Anant, and I'm a master's student from the University of Alberta in Canada. So today I'll be presenting my research, which is on the design and development of a scintillation detector. So on the slide here on the right side, you can see a picture of the design detector. And this is supposed to fly on a small satellite mission that's being built out of Canada called Radicals. And I'll be explaining a bit more about what this mission is, what this detector is, and the story of how we made it. So this slide shows an overall overview of the detector. So it was conceptualized about a year ago. And then we went through a process of designing it through the different stages of PDR, CDR, making a detector. And we got a flight of opportunity on a NASA sounding rocket from the Wallops flight facility, which I'll be explaining more. And we integrated on that rocket. I was there in June. And then we're planning to launch it, which is next week. So after finishing this, I'll be going there to participate in the launch. And then eventually, if it works well, we'll fly it on the Radicals mission. So before I explain about how of the detector, I would like to explain a little bit about why. What is energetic precipitation, and why do we care about this? Why do we want to measure this? So to give some of the motivation, the Earth is surrounded by regions of charged particles, which you may all know as the Van Allen radiation belts. So there are predominantly two belts. One is the inner belt, which mostly consists of protons, and there's the outer belt, which mostly consists of electrons. Sometimes what happens is these trapped electrons, which are in the outer belt, can enter into the Earth's atmosphere and deposit energy into the Earth's atmosphere through a process known as energetic particle precipitation. So this is a little bit different from rain, which is normal precipitation. These are highly energetic electrons that enter and deposit energy into the Earth's atmosphere. This has been shown in past studies to have a significant role in the ozone depletion in the middle atmosphere. And that happens by generation of these radicals, nitrous and hydrogen oxides, which then cause a depletion in the ozone. That depletion can then have effects on overall heating up, as well as air surface temperatures in the polar regions. So understanding what this phenomena is and having a more quantified measurement of that is very important. And then secondly, from the industry perspective, it's important to know the physics behind this process so that we can better understand how to shield our spacecraft avionics for even LEO and further missions. So this is a slide that briefly shows the physics behind energetic particle precipitation. So the figure shows a electron moving around the magnetic field line, and it undergoes what is known as bounce motion. So these electrons are trapped, and this happens if the velocity vector is outside the loss cone region which is shown in the figure. During geomagnetic storms, what can happen is that these velocity vector of the electron can go inside the loss cone, and that causes the particle to precipitate and enter into the Earth's atmosphere. Just as a disclaimer, this is not a simulation. This is a quick animation I made up sitting in the 24-hour flight from India to here. So this is, in reality, the particles are gyrating in the order of milliseconds, and the bounce happens in the order of seconds. So to better understand this, we are, first of all, there are many open questions about this precipitation process. First of all, what is the energy spectrum of the electrons that are precipitating? What is the flux? What is the causal mechanism and all these? There have been previous missions, but I will be explaining due to limitations in the instrumentation available. These questions have not been answered perfectly. And particularly, one phenomena that's of interest to the scientific community is of microbursts. So this is shown in the plot on the bottom left, where you can see these hair-like structures on top of the normal flux. So these are within milliseconds of time, and they have order of magnitude increase in flux during that small duration. So to understand this, we need a fast detector that can respond very quickly and has a wide energy range. So we are thus building a mission called Radicals, which is shown on the top right. That's a low Earth orbit mission. And then we're also flying this detector on a sounding rocket, which is shown in the figure called PEPPER-X, which stands for Payload for Energetic Particle Precipitation, Education and Research. We're proud of that acronym. So this figure shows different points around the trajectory of the electron that we can measure it. One is the equatorial region, the low Earth orbit, through sounding rockets, and then ground-based measurements through balloons and imagers. So this slide shows basically what I was talking about is what are the requirements of such a detector. And additionally, there are the constraints that are associated with a CubeSat platform of low power, low mass, and low volume. So based on these constraints, we did a survey of possible options. And one option was to use a scintillation-based detector. These detectors are used for ground-based laser plasma measurements, and previous missions have tried to use it for gamma rays and X-ray measurements. And in this study, we are trying to extend this methodology for in situ measurements of electrons. So this animation sort of shows an incoming electron hitting the detector, and then that detector generates multiple photons, and then these photons then hit the multi-pixel photon counter below the detector, and then that can be counted to know how many photons were there, which is then related to the energy of the incoming electron. Again, this animation is slowed down, so imagine this animation but a billion times faster, because these scintillations happen in the order of nanoseconds. So that's the operation of the detector. And then the next question was how to design this. So what is the size? What is the scintillator material? What is the detector? So all these were different considerations. I'll be explaining a few of them. Particularly to decide the size, if we make the detector bigger, we can have a higher energy range, but we lose out the flux that can be measured because the detector will saturate. So we compared this for a few different sizes, as well as a few different count rates that the electronics can handle. And based on that, we narrowed down a size of 0.5 centimeter for the first version of the detector, which can measure up to 3.5 MeV, and a count rate of 10 to the power 5 for the flux. On the left is shown a simulation of the geometric factor that basically relates the incoming flux to the counts generated in the detector. Following that, this slide shows an exploded view of our instrument. So there is a top cover, which is an aluminum cover at the front of the detector. That is a light tight cover. So basically, since the scintillator generates photons, it is important to shield the detector from external photons coming in. And then behind that is the detector itself, which is a 0.5 millimeter scintillator crystal on top of a silicon detector. Additionally, for the rocket flight, we had 2 of these detectors, and that was added so that in case there is no real geomagnetic storm during the rocket flight, the other crystal is a special naturally radioactive element, lutetium, and that generates calibration signals every few milliseconds that we can use to prove the overall functionality of the instrument. So we have 2 sets of detectors, and then this is a time lapse we filmed during making of this instrument that shows the different boards being populated, and then now a cover will be added to finally enclose. It has to be made sure that we do not touch this scintillator crystal because that's coated with aluminum. And if you touch it, you're going to most likely break it, and my master's thesis defense would be delayed significantly. And then this slide then shows the electronics. So this was a very key part of the instrument itself because the detector generates these analog signals, but finally we need a histogram of the flux and the energy spectrum. So for that we had designed a power system, processing system, which is shown here. I will not go into all the details. They're better described in the paper. But they basically convert the analog output of the signal and generate a histogram, or scientifically valuable data product. And we also generate all the required internal voltage. So for the sounding rocket or the spacecraft, just needs to provide us a 28-volt bus, and we convert it to whatever voltages we require. Then after that, we did preliminary calibration. This was definitely one of the most involved tasks in this project, because this involves understanding how does this detector really perform, what is the energy response. And how we do this is we use radioactive sources, which are shown on the bottom right, and we put it in front of the detector, and their spectrum is known. We take that spectrum, the measured spectrum, and we convert it with the known spectrum to know a calibration, approximate calibration of our instrument. Lastly, so the paper was submitted in April, but in advance of the rocket flight, we had to complete all the qualification tests that NASA gave us the directions for. So those were the standard vacuum tests, as well as the vibration tests for the instrument. So those pictures are shown here. And then the sort of final measurement specifications are shown. That shows that this detector performs equal or better in energetic particle precipitation measurements made by previous missions. And then lastly, I would thank you all for listening. And I would first thank my supervisors who are there on the top right. And that picture is taken on the day of the shipment of this experiment. And to summarize, we identified a problem. And then through this my master's, we designed, built, and then we'll be deploying this instrument on a sounding rocket next week. And then once we get the data, we'll analyze that further and then see what modifications are required for the satellite mission. Thank you very much.
Okay, questions? Charlie? No? Mike? Jason? I got plenty.
Nice job on the explanation, and it really helps to understand, starting with the science and then, flowing the requirements down to the rest of the system, down to the actual component. You mentioned something interesting to me. You mentioned that the sounding rocket may not detect anything, so you have a calibration sensor, next to it to kind of make sure you test out the sensor, while it's in flight. That makes me think there's some kind of probabilistic, for the actual radical mission. There's a probability of detection. Have you modeled that, and is there a case to have a constellation of radicals so you can increase your probability of actually getting the data that you want, and then potentially even getting gradient information instead of just in situ information?
That's a great question. So first, for the sounding rocket part, so as I mentioned, these are mostly in the polar regions. Originally, we were supposed to launch on a rocket from Norway, and that mission was called GHOST, and we named it Ghost Pepper. But then that mission got delayed a year, and we are instead launching from Virginia. So that's why the chances of seeing, because the magnetic latitude of Virginia are very low, so the chances of seeing a real event from Virginia are really low. So that's the rocket side. That's why we added the calibration. On the satellite side, this would be a polar orbit. So this would be a sun-synchronous polar orbit. So if there is a geomagnetic storm over the course of a year or whatever our lifetime ends up being, we are most likely guaranteed to see multiple events. And especially these days, the solar cycle has been very active. And then your last point was definitely having multiple of such missions, making multi-point in situ measurements would be ideal. And that way you could understand what is the spatial extent of these precipitation events also.
I love it. You threw in some orbitology in there too, so nice job.
Thank you.
Good deal.